Last time we introduced the cellular chain complex, and of course the chain complex defines homology, and the question is now, what homology does this cellular chain complex actually compute? And not surprisingly, it will compute the original homology, in our case the singular homology we started with, and this is the statement we want to prove today in this video. So actually this statement does not really depend on whether it's singular homology or not, so to be as general as possible, let us start with H star being any ordinary homology theory. Okay, so to recall what we did last time, let me give you the following reminder of the situation. So we start with some, say, relative CW complex. Call it x comma a. And then we know that part of the structure of this object is also the filtration by skeleton, so let us also fix the notation for them with skeleton xn. And for such a relative CW complex, we have defined the cellular chain complex as follows in the last video. Just called it CW star of xa. And this was just defined using the fixed homology theory up here as the relative homology of the skeleton in the degree of interest. Yeah, so the nth homology is defined as the, or the nth cellular chain module is defined as the nth homology of the nth skeleton relative to the n-1 skeleton. So I write this just with stars, as we did this many times. And this is sort of the functorial part of the construction. Yeah, so for every CW complex we get this R module right away. And now comes what depends on a choice, namely if we choose push-outs, yeah, which describe how the n skeleton arises out of the n-1 skeleton by attaching cells. If we choose those, so and a choice of push-outs, let me just write them here, small in. So here we've got our attaching maps going into the n-1 skeleton. And here we've got our disks, dn, and this input gives as a push-out the n skeleton. So if we choose these push-outs, then we obtain explicit isomorphisms of the cellular chain complex to a free R module as follows. So such a choice induces isomorphisms well, from this, actually not only in the degree n, but we found this isomorphism for every index k here, so it induces isomorphism of the kth homology of the n skeleton relative to the -1 skeleton with this direct sum, one summand for each n cell in the CW complex, and then here we had the group hk-1 of the point. Yeah. And I think I said in the beginning that I wanted now an ordinary homology theory, and therefore this isomorphism continues. And this thing is actually then isomorphic to just the following. It's, well, as many copies as we've got n cells of this h0 of a point, in case k equals n, and 0 otherwise, if k is not equal to n. Okay, so far so good. So this was just the situation of last time. And now the theorem we want to prove is the one saying that the homology of this cellular chain complex just is the original homology. So, and To make our life a little bit simpler in the proof, we will assume that the CW complex is relatively finite, meaning starting from this subspace A, we only attach finitely many cells altogether. So suppose X is relatively finite. Then we have natural isomorphisms.
Maybe it's better to say that X, A is
finite. Yeah, that's right.
Because that's the way we defined it.
Yeah. Okay, let me write it that way. Suppose X, A is finite. Okay, then we have natural isomorphisms from the homology of the cellular chain complex. I think you not only defined the cellular chain complex, you also said that the homology of this is denoted like this, didn't you?
Yeah.
Yeah, okay. So then this is already defined as an object. So the relative cellular homology X, A is then naturally isomorphic to the original homology Hn X, A. Yeah, and I mean the case of interest is of course when this H here is singular homology, but right now this is a statement for any ordinary homology theory. Okay, and once more the remark is just, actually we had to put it like this because if we only assume that it's some ordinary homology theory, then we do not know whether the additivity axiom is satisfied. But singular homology does satisfy it, and therefore it's probably good and important to remark that if this homology theory happens to satisfy additivity, then actually we can drop this assumption of finiteness. Yeah? So then XA can be infinite. So since we're working still with a abstract homology theory, we can only use what we know from the axioms. And one of the most convenient tools that we always consider in these contexts is the long exact sequence. And actually this is also what will help us here. So what we will do is we will consider the long exact sequence of the following triple consisting of the n skeleton, I guess, yeah, the n-1 skeleton and our subspace A to which the CW complex is relative, and then the long exact sequence of this triple, which we have concluded from the pair axiom. So we also have a long exact sequence associated with the triple here, and this looks like this. We've got here, say, the big pair xn minus 1, right? Then comes the boundary homomorphism hk going to xn minus 1 comma a. Then next term is the inclusion hk big space xn comma a, and the next one should be again index k and big one, second big one, xn minus 1, and so on and so forth. Okay, and now we will use the isomorphism which I've recalled last time. That was this one. Where is it? So here we had discussed what this group actually is that appears in the long exact sequence of the triple. So hk of xn relative to xn minus 1, that is this bunch of h naught of the points here if k equals n, but otherwise it's 0. Yeah? And as you all know, 0 objects in long exact sequences are very convenient because they allow conclusions, and this is actually exactly what we will use here. So this group hk xn comma xn minus 1, this lies in the long exact sequence here and also here with 1 degree shifted. And we have the effect that if these terms here are both 0, then the arrow in between those two 0 morphisms, this one must be 0 then, this one must be 0, is an isomorphism. Yeah? So we get an isomorphism from hk xn minus 1 comma a to hkxn comma a. And we obtain this situation that these zeros occur in two situations, namely either if it so happens that k is bigger than n, then what do you get? Well, then we get an isomorphism from hkxn comma a to hkxn minus 1 comma a. So that's this isomorphism here. I just write it in the other direction. So it goes to hkxn minus 1 comma a. But of course, if I make n even smaller, then I still have this condition satisfied here. So I still have these terms 0 if I consider the corresponding portion in the long exact sequence. So I get an isomorphism again, and I can make this n smaller and smaller step by step. And inductively, I then arrive in the end at the kth homology of, I can go as far as x minus 1 comma a. All right? And the minus 1 skeleton of the CW complex, that's just this A. And we already discussed many times homology of a space comma the space that is just 0. That follows immediately of the from the pair sequence of A comma A, so this must be 0. And therefore we know that, well, the kth homology of the n skeleton is 0 if this k is bigger than n. Yeah, so an n skeleton does not produce any homology in degrees larger than n. Yeah? That's one thing we can get out of this sequence. And the second thing is we still obtain zeros in case k is strictly smaller than n. And now how can we use these isomorphism in this case? Well, then we've got hk of xn comma a. So now I can, this condition k is smaller than n. I mean, this remains true, or remains a condition I can continue to use if I replace n here with n plus 1. And then I get the isomorphism now in the other direction. So I now increase the degree of the skeleton, and I still get isomorphisms. And I can do this as many times as I want again, because I will still have the zeros surrounding this relevant homomorphism in the long exact sequence. So I get isomorphisms and isomorphisms as many times as I want. But I can go as far as that the skeleton is just the whole CW complex. So now I'm using actually that x comma a we said was finite. So at some point this stabilizes, and the, 1 millionth skeleton will just be the whole space, so I can just write xk x comma a here. Yeah? So the second outcome of this long exact sequence is that if I attach cells of degree at least 2 larger than this k, than the degree of index of interest, then I do not change the homology. Yeah, it stays the same. And so I end up just at the homology of x here.
And you said that this is still true if the additivity axiom is satisfied, if the complex is not finite.
Exactly. So then I could not use this argument, so I could not just say that some skeleton is the whole space. Right. But at that point I would have to work a tiny little to get this.
Let me just make a remark in the case where H is the singular homology. That gives you at least the indication why this might be true. And this has a little bit to do with the point set topology of a CW complex. So if you have a complex subset of a CW complex, it always lies in a finite skeleton. So there's always one n, finite n, such that this complex subset lies in Xn. So the image of a singular simplex always lies in 1xn. So there is a way to argue with singular simplex, with each singular simplex you can somehow, that this can be seen, or a fixed chain can be seen within 1xn. And
I think one can say that the image of such a simplex can only hit the interiors of finitely many cells in the CW complex. think this should be right. No, otherwise, you would get a cover by open sets, which doesn't have a finite subcover.
Right.
Yeah.
Well, okay, so the statement I made was that it
Okay.
lies in a finite skeleton. That's correct.
Yeah, I mean, yeah, in a finite degree. Yeah, exactly. Okay. Anyhow, yeah, so here we just used our assumption, which we have to make anyway if we are not assuming the additivity axiom. But at this point, yeah, one has to make some point-set topological argument to make it still work for singular homology. Okay, so far so good. Now I will need a diagram, which will be kind of big, so I need to make sure I've got some space here. So we'll consider the following commutative diagram. And it's going to be the diagram that actually defined the boundary homomorphism in the cellular chain complex, which we had last time. And you might remember that there we discussed quickly that actually there are two equivalent ways to define this boundary homomorphism in the cellular chain complex. You either use the pair sequence or you use the triple sequence, where you still have this comma A term. And it's the second variant which we will consider here, which will be of interest to us. And this is now the following diagram. So it starts with the n plus first homology of the n plus 1 skeleton relative to the n skeleton. Here we've got our boundary homomorphism going to xn comma xn minus 1. And remember, I mean, this is the cellular boundary homomorphism. Did you call it C something? I hope so.
No, but...
Or did you give it... You didn't assign any name, right? Or did you?
I think I called it with this...
Okay, so I do want to call it C here, as in cellular, so sort of cellular differential, because I want to reserve the usual D or partial operator now for this homomorphism here.
It's fine. What about Cn plus 1 CW?
Okay. Then, yeah, okay. Yeah, maybe it's better. Okay, so the n plus first differential in the cellular chain complex, because here I want to use the notation dn plus 1 for just the boundary homomorphism in the triple sequence hn xn comma a. So this is the, let's make it a bit longer. This is the boundary homomorphism here in the triple sequence of the triple xn plus 1, xn, and a. So this is the one we got here. And remember, the cellular boundary is now just obtained as the composition of this triple sequence boundary homomorphism followed by this inclusion here, which I want to call just in as an inclusion. Okay. So now I can extend this diagram here and go down here with the boundary homomorphism in another triple, named triple, named the triple xn, comma xn minus 1, comma a. So then I end up here at the n minus first homology of the n minus 1 skeleton relative to this subspace A. And now, as before, the next cellular differential, C and CW here, this is just the composition of the triple sequence boundary homomorphism and the inclusion, which I now call in minus 1 to be consistent with the previous notation. And this now goes to the n minus first homology of the n minus 1 skeleton. Yeah, I will need some space relative to the n minus 2 skeleton. And this one here. Okay. And as we discussed last time, well, this was merely the definition of these cellular boundary homomorphisms. Yeah? So these arrows here are just defined by the inclusions, by the compositions here which make this diagram commute. Okay, so now, usual game, we try to find as many zeros and useful information in this diagram we can get. So first things first, here in the vertical term here, we've got the triple sequence of the triple xn comma a, xn comma xn minus 1 comma a. And if we look at the previous arrow here, then this will be starting at hn xn minus 1 comma a, sort of the smallest pair in the triple. And now we use something that we, wait a second, yeah, something that we just discussed. So now the degree here is one larger than the dimension of the skeleton here. And so we use the first isomorphism we have obtained here. This is this case here. If k is bigger, this k here, my pointer is not visible. So if this k here is bigger than this n here, then this is just 0. This is what we discussed before. So actually, this object here is just plain 0. And therefore, this arrow here is 0. And that, of course, in this exact sequence has the effect that the succeeding arrow is injective. Yeah? So we've got an inclusion here. That's one thing. Next thing we can observe here is this arrow here, which also lies in a triple sequence, namely the triple sequence xn minus 1, comma xn minus 2, comma a. So the previous term here, that would be the n minus first homology. Whoops, n minus first homology of the n minus 2 skeleton relative to a. And for the very same reason as before, the degree here is bigger than the dimension of the skeleton. And therefore, this is just 0. That means this arrow is 0, and that means the succeeding arrow here is injective. So two useful additional facts visible here in the diagram. And now we make a claim. So let's get back to black. We make the claim that this morphism In here actually induces an isomorphism from the co-kernel of del n plus 1 of this arrow here, yeah, to the homology at this spot of this chain complex here. So let me just put down this claim. We have an isomorphism from the co-kernel of dn plus 1. And this isomorphism is actually induced by the arrow in appearing up there. So induced meaning I should put a bar on it. And the claim is that this induces an isomorphism going to, well, the kernel of CN/CW divided by the image of the previous one. So CN plus 1 CW. And, well, what's this right-hand thing? Well, that's precisely what we're interested in. It's the homology of this horizontal chain complex, which was the cellular chain complex. So in other words, this is just the nth cellular homology. Okay? So the claim is I can find the nth cellular homology in this diagram as the co-kernel of del n plus 1. Okay. Proof, as usual, when you have a diagram, proof is by diagram chasing. And now, since after all these videos and all these proofs, we have become real experts in diagram chasing, we really do this as a diagram chase, so not writing down anything, yeah, just with bare hands. So let's give it a try. So what do we have to show? We want to show this is an induced isomorphism, so there are three things which need to be verified. First of all, it must be well-defined, this map. And secondly, it must be injective. Thirdly, it must be surjective. So what does well-definedness mean here? Well, it's actually two conditions which we have to verify. So first of all, we have to see that if I start at hn, xn, comma a, and I follow this arrow in, then I end up in the kernel of Cn, yeah? Otherwise, I don't even end up with this map where I want to. That's the first thing we need to verify. And the second thing is well-definedness in the sense of independence of representatives, yeah? So if I take, so what I have to show here is if I take an element from the image of dn plus 1 here and I map it down by in, I want this to be 0, but 0, no meaning in this object 0, meaning it should lie in the image of Cn plus 1 CW. Yeah, that's, these two things is what we have to verify for well-definedness. So first things first, I start with an element up here. I map it down by in here. Why is it mapped by C and CW to 0? So why do I end up by 0 here? Well, that's because I've got a commutative triangle here. So going along this arrow is the same as going along these two arrows. But then I have gone along two arrows in a long exact sequence, which means I already arrived at 0 here. So if I map it up here, I'm also arriving at 0. In other words, I'm in the kernel of C and CW. Yeah, so that's the first part of well-definedness. Second part of well-definedness is I start with an element of the image of Dn plus 1. Yeah, so what's being mod out here in the co-kernel. So if I am in the image of Dn plus 1 here, yeah, and I go down to In, I need to verify that I end up in the image of Cn plus 1 CW. But well, that's that should be clear, because I mean, if I have an element here, I have a pre-image here, then this pre-image is mapped to the same element as if I went down here because of the commutativity in this triangle here. Yeah. So right. So therefore, if I start with an element in the image of Dn plus 1, I end up in the image of Cn plus 1 CW, which means it becomes 0 in this quotient, and therefore I have well-definedness. All right, so now I know that In bar is actually a homomorphism. So if I now want to verify injectivity, I can now use the useful homomorphism criterion. I have to look at the kernel. Yeah, so it's injective if the kernel is trivial. So what does it now mean that I have an element in the kernel of In? Well, that's an element in in this co-kernel here. So it's represented by an element in this homology group here. And being in the kernel now means it ends up in the image of Cn plus 1. It ends up in the in the image of Cn plus 1. So it's 0 in the quotient. So that means, well, if I start with an element here, I map it down here, I find a pre-image here, I can take this pre-image and map it up here. Okay? And now comes the usual trick we have always applied in these situations. I have the original element, I have the new element, I take the difference. If I take the difference and I map it down by In, I end up at 0. Yeah? Because by construction, In maps the two to the same element down here. But now this difference is mapped to 0 by In, but of In we just convinced ourselves it's an injective homomorphism. Yeah? So if it maps this difference to 0, then it already maps the difference itself to 0. So the difference is 0, so the two elements were the same. The original element is actually the element we obtained up here, and that means this element lies in the image of Dn plus 1. Yeah, found a pre-image. Okay, that's injectivity. Last part of the diagram chase is surjectivity. So if we now have an element in the kernel of C and CW here, we need to find a pre-image here. Well, if it is mapped to 0 here, then it's mapped to 0 along this composition by injectivity. But this arrow, we convinced ourselves, is injective. So the only chance that it goes to 0 here is that it's already 0 here. Yeah? But if it's 0 here, it means it lies in the kernel of Dn, and that's the image of In, so I find a pre-image. And that's surjectivity. Okay. That was the diagram chase proving our claim that the co-kernel of Dn plus 1 is actually isomorphic to this quotient here, and this quotient we already commented is just the cellular homology we want to talk about. So of course, finally, what's missing is that the co-kernel of Dn plus 1 now hopefully computes the original homology. By the way, I shouldn't have written x here. I should have written x comma a here. Yeah. Sorry about that. Because it's our relative cellular chain complex here, of which it was the homology. Yeah? So I should put the A in the notation. Okay, so why is now the co-kernel of Dn plus 1, why is this now the nth homology of x comma a? That's the question that remains. And to answer that question, I still need to get back to the diagram and add a little bit of information up here. because what I haven't considered yet is this portion of the diagram. So we really use all the exact sequences appearing here. So this dn plus 1, that was the boundary homomorphism in the triple xn plus 1, comma xn, comma a. So let's look at the next term here. So the next term would be hn of xn minus 1, comma a. And let's look at yet another term. The next thing would be hn. Am I right here? Or should this be hn xn comma a? Wait.
No, I'm also confused.
xn plus 1, comma
you
xn.
look at the triple xn plus 1,
xn comma a. So here was the boundary. So here it should be xn comma a. So no, it should be xn plus 1 here. Yeah. Sorry about that.
xn plus 1a, yeah.
Yeah. Sorry. Yeah. This is hn xn plus 1 comma a, and the next term should be hn xn comma a. Right. Ah, no. Yeah, I'm so confused. Okay. It should be xn plus 1 comma xn. Yeah. Okay. Right. Right. So you always have to think it starts with a
once more. Can you scroll? hn plus 1, yeah. Okay.
So this was the one always has to think the biggest pair, then the middle pair, then the smallest pair. So this was the biggest pair, this is the smallest pair, this is the middle pair, this is the biggest pair. Yeah, so now it should be right. Okay, so far so good. So now we've got hn of xn plus 1 comma xn, and now we use again what we computed above there. Yeah, we computed the homology of this pair here, and it was only non-zero in the degree that's written here, but we are one lower here, so this is just 0 for an ordinary homology theory, as we are assuming here. So this being 0 as an object means this arrow is 0, and this arrow means that being 0 means that the previous arrow here is surjective. Okay, so here we've got a surjective homomorphism. A surjective homomorphism implies by the sum of the Noether theorems that this group here is actually isomorphic to this group mod out the kernel of this homomorphism. Yeah? But by exactness, the kernel of this homomorphism is the image of this homomorphism. So what I really get here is it's the homology, it's this object here divided by the image, and this is precisely by definition the co-kernel of dn plus 1. Yeah, so let's put this down. Proof by diagram chasing, and we have the co-kernel of dn plus 1 is isomorphic to, where is it? To this object here. So that's the nth homology of the n plus 1 skeleton relative A. Right? And now we use the second isomorphism we concluded as a preparation up here. That was this part. Yeah? So that's the case. The degree here is smaller than the dimension of the skeleton in question. And in this case, we see this is just the homology of the whole space. So actually, as we wanted, it turns out that the co-kernel of del n plus 1, that is isomorphic just to the homology of x comma a. All right. So we have now proven that this homomorphism in does indeed induce an isomorphism from the original homology to the cellular homology, and there was also a naturality statement in the theorem. So let's put down what happens about that. But there I'm lazy enough to say that naturality follows from the naturality statements in the long exact sequences. Yeah? So, and naturality follows from naturality in the various along exact sequences. Okay, so maybe quickly what I mean by this is, well, if I had a cellular map now from a relative CW complex x comma a to some relative CW complex y comma b or so, what I would get is I would get a second diagram of exactly the same kind, maybe like a meter behind the screen here again, yeah? And the continuous map of the cellular map of CW complexes would give me arrows in the deep into the other layer here, yeah? And would have a commutative 3D diagram with these diagrams here in the plane, and everything commutes, yeah? And out of this, by taking homology here, I also get then an isomorph, maps commuting with these isomorphisms here. Right, so this concludes the proof of the theorem. So block, and the video is over.